Alright, welcome to this computational topology tutorial series. So, in this series we're going to develop a bunch of topological data analysis algorithms so that we can analyze data. And in this particular, sub-series here, we're going to be working with cubical data. So, cubical data, essentially images, videos, that kind of stuff, is really what we have in mind. So we got to design our framework to be able to basically import that type of data, and then so we can, use our algorithms on it. So there's going to be a bunch of different components to this thing, and in this video we're going to first lay out some of the data structures. And, well, you can see here I have this empty folder right now with these three empty folders in it. And what we're going to do is we're going to make a matrix class. That's matrices are going to kind of be the general object that we're going to be working with. It's essentially linear algebra, so matrices are really the important thing there. And, yeah, I know most people have done this a million times already if you're in doing scientific computing. But we're going to do it here, and we're going to try to make our matrix class as general as possible. So we're going to have templates for the data type. That way, in case we have data which is integer valued or double precision or even, complex numbers, we don't want to have to write the same code over and over again. We'll let the compiler handle that for us. So, I guess without further ado, let's go into our little project here. So I'm using Visual Studio Code. Again, you can use whatever you want. And I have my folder open here. And so I'm just going to create a new file. We'll call it matrix.h. And this is like the central data structure in this whole program. Now we're gonna be making other data structures as we go along, but it's good to kind of get this done and out of the way. So I do want to use a namespace for this because this has to do with cubical complexes, cubical data. So I can just call it cubical. And again, you don't have to do this, but I like it because it kind of organizes the framework. And of course we're going to make a class called matrix. And you could make this a struct if you want, but there's going to be a lot of different methods, so I don't know. The class seems a little nicer to me. And like I said, I want to template this because we could have a bunch of different data types that we're going to be manipulating, and so I don't want to have to rewrite the same code for integer or double precision values. So for those of you who don't know or are new to this template thing essentially just tells the compiler to compile or to basically write the code for us whenever we tell it that we want a instance of a particular type. So later on, I may do something like this, and when the compiler sees that, it's basically going to take all of the code related to matrix or anything that has a template T having to do with matrix, and it's just going to write that code replacing the T that appears everywhere with double. And that's really useful because I can also do this. And the compiler will also, again, copy all of this stuff, replacing T with int. And so it'll overload everything for me, and I don't have to go in and do it myself, which is why templates are really useful. Now, of course, I'm going to have some constructors here, and I have my the generic stuff. We'll just get that out of the way. And I'm going to have a few more constructors that I want for a matrix. One of them is going to take the number of rows and number of columns, and I'm going to do everything in row order, row major order. You could do either row major order or column major order. It doesn't matter. It's not going to make any difference. As long, you have to specify the actual methods operating on matrices depending on which one you choose. So if you wanted to go ahead and do it row major order or column major order, you would have to do things a little differently than I'm going to do them, because the multiplication is going to work differently. But anyway, so this is going to be row major order, and the number of rows that I want to specify is going to be given by n, and the number of columns is m. So I want to create something here to actually keep track of that. So that way I can just get the size. I don't have to necessarily access the container of the values itself. So I'm just going to call this n and m. And of course we'll have getters for those. We'll probably have setters too. I'm not necessarily sure if we're going to be worried about resizing our matrices for any reason. I think once we make one, it's just going to kind of be fixed. But we'll put it in there anyway, just in case that changes. Alright, so obviously the other thing that we need here is the container for our values. We need some kind of 2D array that's going to hold all of our type T. That's going to be our matrix. So there's, many different ways that you could do this. You could use C-style arrays, by having a double pointer. Of course, these things are not fixed in size. At least not, within the class itself. I want to be able to basically make any size matrix I want at any time. So I'm not necessarily going to go with the C array approach, although you could do it that way. A more cleaner way would just be to use std vector from the standard template library. And this thing, of course, keeps track of the size for you. So, we don't really need these guys here because this is going to keep track of it for us. But instead of, having nested calls to get the size, it doesn't hurt to just have these extra variables here to access them when I want them. Now, this is basically a 1D array of a set of 1D arrays. And, other than, this is pretty much basically the same as a C-style array. It wraps a C array, except that there are an additional three pointers for every one of these vectors. So every time I make an std vector, I'm going to create a C-style array, but then I'm also going to allocate 3 pointers at the beginning of where that array is stored, and that's going to tell me the beginning, the end, and the size of the array. All right, so that's std vector always creates those 3 pointers. Now, if I were to just make an std vector like this and put some data in it, well, this thing would store the data sequentially on the heap. So you'd have your 3 pointers, your 3 pointers, begin, end, and size, and then you'd have your data, right? And that would just be sequential, right? Whatever's in that vector. And this gets allocated every time you create one of these. Now, the unfortunate thing is when you create one of these, now if I nest this guy inside of this std vector, Well, now the data is not going to be sequential anymore. It will be for each individual one of these, but each of these could be located somewhere else on the heap, right? Somewhere else in memory. So this guy, yeah, it's gonna give me a pointer to each one of these, but now the data is no longer actually sequential, so I have to keep jumping around. It's not a big deal for us, but if you're doing something in which you actually want to look up the data sequentially, well, that can be a little bit of a problem. We don't really care though, so it's not a big deal. Now, I really don't enjoy writing this out every time I want to use it, so I think instead I'm just going to create a type def, and I'll just call this array. So I'm going to say that this is type name t, and this is going to be what's called an alias. Basically, it says every time I say array, what I want is the compiler to replace that with that. So now when I come down in here, I can just replace this with array t. Right, and this array t is going to show up in a lot of places, and so instead of typing this out every time, I just created an alias for it. So it's exactly the same thing. Okay, good. So now I have my 2D array, which is just nested vectors of type t, and that's my data. That's where all my data is. And then I have these two guys. Okay, good. So with this here now I can create an additional constructor in which I actually take in one of these. And so that this will just assign my data to whatever I pass in. And finally, I want one additional constructor, and for now I'll just leave it like this. Basically, I know at some point we're going to want to extract data from files, and so I'm just putting this here for now to remind me that I want to actually implement this somehow, and we'll figure out how to do that later. For now, I'm just going to leave it like this. It may have other parameters in the future. I'm not sure yet. So other than that, let's just add a few of these. And so I want to be able to get the number of rows. Of course, I want to return that const because I don't want to change that just by getting its value. And likewise with the number of columns. And that's pretty much it. Of course, we have to have some way of accessing this guy. And what I'm going to do is, well, we're going to write a whole bunch of operator overloads that will manipulate these matrices. And in particular, we'll have operator overloads for accessing this guy. So let me show you how that works. So, for example, if we want to access the values in this matrix, I don't want to have to do something like, say we do this. We have our matrix that has some values in it. I don't want to have to type get val ij. Although, we could do it that way. It would be much easier if I could just say this. And that would just refer to, this would automatically do the same thing. And so then when I'm writing, more complicated code, I don't have to write this get value every time. I can just do this. And furthermore, I don't want to have to write, anytime I change something, I don't want to have to write this either. So I can also have this mean the same thing. So for example, if I did this, that would set the value of m at ij equal to 5. However, if I wanted to say x equals ij, well, then that would set x equal to whatever the value is in ij. So I can have the parentheses do both things. And the way we do that is by overloading the parenthesis operator. So to do that, both of those are specified in a similar way. So the one that actually gets the value, that returns the value, we want our value t, and we're going to say operator. And this is the operator that I'm overloading, the parentheses. And in this, I want to specify an unsigned integer I and j, and that refers to the row and the column that I want to actually retrieve. And I want to return that const, meaning I don't want this operation to return a reference to ij, because then if later on I say something like, I don't know, x plus equals 1, that could actually change the value in here, and I don't want that to happen. So just as a precaution, just to make sure that I don't do something like that, I'm going to declare this as const. So this one will actually retrieve that value and set something equal to it. If I want to change the value in the matrix, well, then I have something similar. What I am going to do is pass a reference, and basically everything is going to be the same, except this is not const, obviously, because I want to actually be able to change its value. So this one will return the value, a copy of the value. This one will return a reference to the value. Okay, and so now that parentheses mij has double meaning. So I can either use it to set the value or to set something else equal to it. Okay. And of course, you know, we have to specify all this stuff later. For now, I'm just writing down the declarations. Or the declarations. Now, with matrices, there are many other things. There are many things that we can do with them. For example, we could add two matrices together. Two matrices that have the same number of rows and columns, of course. So we'll have to make sure that that condition is satisfied. And here we're going to have a similar thing as this. We're going to have one method which will return a new matrix. So I'll explain what this does in a second. I just want to write this out. So basically what this is going to do is, well, if I have some matrix M and some matrix N, then I want to make a new matrix R by doing something like that. So if M is a matrix, N is a matrix, I can create a new matrix by doing the following. And this will not change what's in M, and it won't change what's in N. Hence the const here, when actually specifying other, which is N in this case, and the const here, which refers to, you know, me, whatever matrix I'm putting in the first slot. And so this won't change what the values in here, but it will add them up and spit out a new matrix whose entries are the sums of the entries of the original two. So that's what that does. The other thing we could do is, well, I could take a matrix. Instead of giving me a new one, I could say let M equal whatever it is plus the values in N. All right, that's another thing I could do. So I could actually change the current matrix by adding to it another one. And that we would do in a similar way, except we're not going to return anything. So that's void. But again, I don't want to change the second matrix, so I'm going to make sure that that's const. And you can see this kind of looks, you know, a little like this pattern here. Okay. You know, with addition, of course, we can also do subtraction, which is the same thing, right? So operator minus this time, and minus equals, and that's basically just going to be copy and paste of whatever the code is in here, except replacing plus with minus, right? No big deal. Now, the other, the thing that we do most of the time in matrices, why they're useful, is to multiply them together. We can, represent many different types of algebraic operations by multiplying matrices. And so the multiplication, it's really the more, I don't know, it's the most common thing that we're going to do with them. And again, this is going to have a similar set of operations. If I want to multiply two matrices and return a new one, I'll do that. And again, if I want to multiply my current matrix with another one, then I'll do that. Okay. And that one this will have to be a little more careful with, because it's slightly different. Now, the only other thing I can really think of that's going to matter is scalar multiplication. So instead of multiplying by my matrix, I'm going to multiply by a value, a real number. Or, well, it doesn't have to be a real number. It could be an integer. It could be a complex number. It could be anything. Whatever it is, it's one-dimensional. And so it's a scalar. And again, I can return a new matrix, or I could just multiply the current one by a scalar. Now, if you look in other places for people that make these matrix classes, you'll see things like, oh, I don't know, matrix T operator divide constant matrix. You'll see something like this, where you're dividing a matrix by another one. Well, that's just ridiculous, because that's not actually a defined operation. Really, I mean, it's a convenient thing if you want to say you have two matrices which are the same size, and you want to take every entry n in matrix M or n, and divide it by the entry m in matrix M. Entry by entry, if you wanted to do that, then that's what you would write that function for. But it's just not an actual thing. And so I don't see why we're ever going to need it. And furthermore, if you want to divide by a scalar, well, that's certainly well defined, but we could just multiply it by 1 over the scalar if we wanted to do that. So there's no need to overload that operation either. Let's just keep everything consistent with what is actually defined mathematically. So as another tangent example here, you might have something like a vector class, where you experience the same thing. You say, I want to take a vector v and divide it by another vector w. Well, that's not a thing either. It doesn't make any sense. So we're just not going to do that. So now we have all of these operators overloaded, and a good amount of stuff defined here. So we're actually going to go in and start to define our methods. Now, because we're using templates, I can't just create a new file here called cpp matrix.cpp and put everything in there and compile that cpp file, because when I try to do that, the compiler is not going to know what to do with this definition, with these template definitions. So either we have to declare the code or write all of the definitions in the header file, or if I do want to use a CPP file, I have to include it, in here. I would have to do something like that. Otherwise, the compiler wouldn't, if you tried to compile this guy as a separate file, it wouldn't know what to do with these definitions. So that's one of the downside of using templates. You have to either do this kind of weird thing here, or you have to actually declare everything in the header file. I'm just going to put everything in the header file because it's fine. So here we have to actually specify our definitions, and every one of these methods, because this is a template, has to begin with that. And I'm just going to do them in order. So our default constructor, I'm just going to set the size to 0, because sometimes we're going to have, in other methods, we're just going to create matrices using the default constructor, and I don't want these numbers to be undefined, because that could screw things up. And so just to kind of safeguard against that, I'm just going to set them to 0 in the default constructor, and that's it. Right, the mmat I can leave empty for now. That's fine. For the default destructor, I'm not going to do anything here. I'm just going to leave it empty for now. And that brings us to our one constructor, where we have the actual size. Right, so this is given unsigned int n and m. We're just going to set n equal to n and m equal to m. Easy enough, right? And then we have the one where we actually feed in a array of type t. And for this, well, we don't want to just make a copy of this guy. I think what we want to do is just move whatever it is, move that actual object into our member here. So this std move is going to take whatever this array is that we pass in, and it's just going to move it into mmat. So it's not going to make a copy. And that will actually also speed things up tremendously, because if we start dealing with these really large matrices, and we go to actually dump one of these in here, if I just set this equal to mat, if I just did this, then it would actually create a copy, and that could take a long time, especially if we have millions. Well, not a long time relative to us, but if we're doing it many times, it could slow down the program. So instead, we're just going to move. So we got to keep that in mind when we're doing this. We want to make sure that we're not. We want to make sure that whenever we pass something in here, that we know that it's going to be destroyed. The original thing is no longer going to exist wherever it was. It's now going to be moved to represent the pointers that are associated with this thing. Okay, so we just have to keep that in mind. As far as the size goes, well, now that we have an mmat, we can just set these. And I know that, well, yeah, no, this is fine, because this is always defined to be this, which is a vector of vectors. So if we try to pass just a single vector into here, it's not going to like it. And so we don't have to worry about this giving us a memory problem, because this is guaranteed to have at least one vector inside of another vector. So this is fine. And then for now, we'll just write this guy, and we'll leave it empty. We'll worry about filling that in later. And of course, you know, I have to actually include string and include vector. And I might as well just put iostream here because we're going to need that later. All right. Okay, so that's it for the constructors. Now all we got to do is write all these operator overloads. So, just doing these in order. The first one is the overload of the parentheses. So this one's actually going to return our, you know, just a copy of this, whatever's in here. Oops. Okay. And here's where we actually have to start worrying about doing some error checking. Because, you know, I mean, in principle, I can pass any numbers I want into this guy. And I don't want to just blindly say, all right, return. Because if I give something that's out of bounds, well, then my program's going to crash. And that's not going to be any good. Well, it's not necessarily going to crash, but I'm going to return a value, which is just going to be some garbage. Because it's going to look somewhere else in memory in which there is no value. It's just something else. So I don't want to do that. So I just need to have something which says if the row value I give is greater than or equal to the number of rows, or the column value I give is greater than or equal to the number of columns, then I just want to say, all right, for now I'm just going to do this. Error indices I j exceeds matrix of size n m. Okay, let me just clean this up a little so we don't have to. Okay. So we're just going to say, hey, if you try to do this, I'm going to print out this error message. And then, well, we still have to return something. So I think for now I'm just going to return the first value. You know, we'll come up with a better system of handling this stuff later. For now I'm just going to do this. Now, if that doesn't happen, then we do actually want to return ij. And there we go. Okay, so that should work. And with respect to the reference, it's going to be exactly the same thing. So I'll just copy this, paste it, and that gets changed to an ampersand, and we have no const here. And that's it. Right, so this will do exactly the same thing. However, this function will know to actually return a reference instead of just the value. Right, so we don't have to do anything special there. Okay. So those are the access methods. Now we want to actually institute addition. So, if we take a look, we have our two different types of addition. The one that returns a new matrix, and in that case, we have this definition here. And because we don't want to change the values that are in either of these matrices, we have to basically create a new array here whose values will be filled with the actual sum of the ones that are in these two. Now, again, we want to make sure that some condition is satisfied when we do this operation. So the number of rows and columns for each has to be the same. So we definitely need to check that. So if the number of rows is not equal to the number of rows of the other, or number of columns is not equal to other.getM, then like before we need to do something where we say, I don't know, for now we'll just say error, matrices are not compatible. I think that's good enough for now. Again, we'll come up with better checks against this later once we kind of get going. And, you know, eventually I want to put some kind of logging system in here so that, you know, when we have this great big program which is doing all of these operations, and once things start to get really complicated, you know, this is not going to do it for us if we run into a problem, because this doesn't tell us anything about where the error is happening or what the values are that we tried to access or anything like that. So we're going to have to make this much more robust to be able to identify actual problems when they show up. I'm just doing this now just to kind of remind myself that we need to do that. But in any case, so we have this, and if this happens, I guess for now I'm just going to say the temp equals, I'm just going to copy our matrix and plug it into here and then return it. And that's if things fail. If things don't fail, then of course we want to actually fill this temp up with the values. So we're gonna iterate over the rows and the columns, and when I iterate over the columns, I want to actually fill up a row vector. So I'm going to do this. Then I'm going to say unsigned int j, 0, j is less than number of columns. And I'm going to fill up this row vector with this matrix entry plus the other matrix entry. So I'm iterating over every row, and in every row what I have to do is I have to iterate over the columns, and I'm going to take each entry in each column in this particular row that we're in and add them up, and I'm just going to push that back to this temp row. So this temp row is going to collect all of the sums of each column for whatever row I happen to be on. And then once that's done, then I actually want to say temp.pushback, temp row. Okay. And that should be it. Yeah. Oh, of course we don't want to return temp. We want to return a new matrix with that new array t temp that we specified. Okay. Good. All right. So then the other one, of course, is plus equals. And plus equals is basically going to be the same thing here. So I'm just going to copy this. And this becomes void. There's no const. And we actually don't have to create a new array. So I'm going to get rid of that. And if this happens, well, I'm just going to return. So I don't have to do anything. Of course, that's plus equals. And I also don't have to do this. I don't have to do this. And I don't have to do that. The only thing I have to do is say this plus equals that. So I iterate over every value, and I just add the other values to each value in my array. And that's that. Easy. Okay, now we have subtraction. So subtraction is exactly the same thing, except with plus changed with minus. So I'm just going to go plus. Oops. I'm just going to change it to minus. Change this to minus. This one. And this one. In there. Easy. Okay. Now comes the hard one. So now we have to do multiplication. And again, we have two types of this. Let's see. Okay. Now, I'm just going to copy this part here. Yeah, I'm actually going to copy all of this. The thing that's going to have to change, oops, this is times. The thing that's going to have to change is what happens in the body of this. So we are going to iterate over every entry, but this time we need to actually add another set of loops based on the way that matrix multiplication works. So this is going to be unsigned int k less than m k plus plus. And then I have to make some changes here, and I'll explain what these are in a minute. This is going to be other.getM. And what I'm going to end up doing is temp val is going to end up being the multiplication of these two entries. And then at the end, I'm going to push this back with temp val. There, done. So what am I actually doing here? Well, it's kind of hard to explain without actually drawing or writing out what's going on. But we're basically, every new entry in the matrix is going to be, the sum of a set of multiplications from the old matrix. Right. So before we didn't have this inner loop here. Right. We just iterated over every pair of indices. Now for each pair of indices in the new matrix, specifically ij, so for each ij in the new matrix, that's going to be a sum of products over these multiplications. And in another video, I'll show you, what it actually means to multiply these two together. Now, this new matrix is going to have a different size, in principle, than the original two. It's now going to have, so this guy could have some size n and some number of columns m, and likewise for the other one. And actually, you have to change this condition here. So the only thing we need to impose is that the number of rows in the second matrix equal the number of columns in the first. That's the only requirement. And when we do that, we actually do this multiplication. The number of rows in this guy is going to end up being equal to the number of rows in this one, right? So those are going to be the same, but the number of columns is going to be equal to the number of columns in the other matrix, right? So I'll explain this in another video, but here it is. This is the actual matrix multiplication. And then we just want to copy this for the times equal. And for there, again, it's void. There's no const. And we don't have to do this. We don't have to do that. We can just say return instead. Times equal. And for here, we don't have to do this. We can just say, oh wait, actually, no, we do have to do that. So we are going to do all the same thing, except we're not going to say return here. We're just going to say this is going to be that new matrix, right? So we can't just go through here and do the adjustments, because we actually have to sum over them. And so if we change something in here, then it's going to affect the actual calculation. So we have to do this first and then just set this at the end. Okay, easy enough. Finally, we have scalar multiplication. And yeah, this is really the easiest thing to do here. Oh, and of course we want to set that to const. And not times equal. Again, we're going to create an array. And we're going to loop. And of course we do this. And we're just going to say our temp row, we're going to push back whatever this mij is times the scalar. Easy. Now, of course, we want to push back that temp row, and at the end return this guy. Okay, so all I did was just iterate over and multiply each of the entries by that scalar. That's just the way it's defined. And of course, we do the same thing for the one that doesn't return a new matrix. Get rid of that. This we don't need. That we don't need. That we don't need. That we don't need. And we just have to do this and put a times equal there. Alright, so that's pretty much everything that we're going to do for now in this video. So we have all of our basic matrix operations finished. They may not be exactly optimized. We may go back and change a few things to try to make this work a little faster. Especially in the multiplication. There may be a better way to do this. We'll see. But for now, this is fine. And I just want to add one last quick function so that we can visualize what's actually going on and we can do some examples. So I'm just going to make a print function down here. And this is just going to print out the actual entries. So this, and I want to start out with a new line and then a bracket. And then we're going to actually go over each of the entries here. So we'll just do this quickly. And I want to do this entry and leave a space. And then if we happen to be, just to make this nice and neat, if we happen to be at the last row, the last If we are at, what do I want to do here? If I is equal to m minus 1, then I want to do that. Yes. Wait. Is that what I want to do? I think so. Yeah. And then I'm just going to leave a space at the end. There. That's it. Okay. So now let's see if our matrix operations are actually working like they're supposed to. So I'm just going to go into source and create a main.cpp file. And in here, I'm just going to include matrix.h. And what do I want to do? Let's see. Right. So I want to just make a couple examples here. So this is going to be double. And I'm just going to fill this with, I'm just going to make this an identity matrix 3 by 3. Main, how did that happen? M. Okay. Why are you getting mad at me? Okay. Interesting. Alright, so I'm gonna want to print that out. So let's see if that actually works. Let me return 0 here. And open up a terminal. So we're in our workspace. And in here, I'm just going to go into source. And okay. Matrix was not declared in the scope. Interesting. Ah, duh. Because I put it in a namespace and then I didn't actually include it. Okay. Let's see if that works. Okay. Ah. Well, I'm a moron, because I put this inside of matrix. I didn't want to do that. It's not part of that class. There we go. Alright, this should work now. Yep. And it did exactly what we wanted. It printed our little identity matrix here. So that's cool. Now let's make sure that the other operations actually work. So I'm going to come back into main. I'm going to make a couple other matrices here. M2, I'll call it. And let's see, I'm going to make this is a 3 by 3, so I'm going to make this one a 3 by 2. So the rows have to actually be the same as the number of columns if I want to multiply them. And when I do this, I should get back another 3 by 2 matrix when I multiply this by the identity. So let's see, 5.0, 6.0. Okay, and I'm just going to print this one. And then I'm going to say, all right, I want a new matrix M3, and this is going to be M times M2. Then I'm going to print that guy. And let's see what happens. Bam. Exactly what we wanted. So here was our identity. Here's our M2, 1, 2, 3, 4, 5, 6. And then when I multiply them, I get back exactly what I expected, right? It's just the identity multiplying, so I just get back the same thing. Now let's make sure that this actually, right, this is kind of a trivial example. Let's, instead of 1s, let's put 2 everywhere. And when we do that, well, I should get back. Yep, you get all the elements multiplied by 2. 2, 4, 6, 8, 10, 12. Good. All right. So I'm not going to test the other methods for now. I'm just going to leave this the way it is. I just want to check one last thing, and that'll be if I actually want to do my scalar multiplication. So if I do this, then it should multiply everything by 5. And yep, that's exactly what happened. 10, 20, 30, 40, 50, 60. Good. So that's doing what we want. And again, right, I could have used anything I wanted here. These didn't have to be doubles. You can change this to int, and it'll still compile. Except now, ooh, well, I spoke too soon. Oh, of course, I'm putting zeros here. Let me get rid of these. And that should work. Yep, same thing. Of course, when I had it print the floats, it didn't actually print the trailing zeros. But they were actually doubles, so. So I guess that's it for now. I think next time we're gonna clean up the error handling, and then we'll probably start implementing some more matrix methods to do various things like swap columns and rows and things like that, because that's what we're going to need to actually implement our algorithms. And then at some point we're going to have to write that constructor that took in a file name. But until then, I'll see you next time.